Welcome friends to this lecture of soil science and technology, and in this lecture we will start from the slide where we left in last lecture. And in the last lecture we started about the methods of measuring the soil content, and today we'll try to finish that. And also we'll today this is the last lecture of week 2, so we'll try to show you some numerical examples regarding the uh, bulk density, particle density, and soil water content and porosity, which you already have covered. So, let us start with the methods of measuring soil water content. So, we have already covered this slide in our last lecture. So, we should move from here, and let me show you some measurement of water content. Now, measurement of water content, as you know, the direct method is called gravimetric method. So, measuring water content can be done by this gravimetric method, and water may be evaporated from soil by heating at 105 degree centigrade to a constant weight. So, what happens? We take some moist soil samples, moist soil from the field, and we dry that moist soil, and we take the moist soil weight. Let us see that let us assume that it is mass of moist soil, and then we dry the soil at 105 degree centigrade overnight, and as a result the water evaporated, and then we get the mass of dry soil. So, gravimetric moisture content, which is W, which is denoted by W, can be expressed in terms of mass of water evaporated in gram over mass of dry soil. Now, we already know the mass of dry soil, that is MD, and mass of water evaporated can be calculated by MM minus MD. So, if we subtract the weight of a dry soil from the weight of a moist soil, will get the mass of water evaporated. And so, this is one of the major method of measuring water content. However, there is another direct method, we call it volumetric moisture content, and volumetric moisture content is generally expressed in terms of theta. And volumetric moisture content is basically volume of water evaporated over the volume of soil, and the relationship between volumetric moisture content and gravimetric moisture content is theta equal to W, which is the gravimetric moisture content, multiplied by bulk density of a soil over density of water, which is generally 1. Now, bulk density of soil, which is dB, you know that mass of dry soil over volume of soil. So, it is basically the bulk volume of the soil. So, by using this formula, we can convert from volumetric moisture content to gravimetric moisture content and vice versa. So, these two methods are direct method for measurement of water content. So, let us see one example. So, if you see that a soil is sampled by a cylinder measuring 7.6 centimeter in diameter and 7.6 centimeter length. So, calculate gravimetric and volumetric water contents and dry bulk density using the following data. Now, you can see already it has been given that weight of the empty cylinder which we used for collecting the soil from the field is 300 grams, and weight of cylinder plus wet soil is 1000 grams, and weight of cylinder plus oven weight, which is 100 after drying 100 over dry weight, that is after drying at 105 degree centigrade, we get 860 grams. So, let us solve this. So, we already know that the volume of the cylinder can be calculated by pi r square is the formula, where we already know the value of r, that is 7.6, and so using that we can we calculate this 345 centimeter. Now, 345 cubic centimeter or cc. Now, we know that weight of the wet soil is weight of the wet soil is basically the weight of the cylinder plus wet soil minus weight of the empty cylinder. So, that will be 700 grams, and we know, and the weight of the dry soil is 860 grams, minus 300 grams, which is the weight of the empty cylinder. So, we get 560 grams. So, dry bulk density is basically we are getting weight of the dry soil over the volume of the cylinder. The volume of the cylinder is 345, and it is ultimately we are getting 1.62 gram per cc. Now, gravimetric. So, once we calculated this dry bulk density, now we can calculate this gravimetric moisture content. Now, gravimetric moisture content, the weight of a moist soil minus weight of a dry soil over the weight of a dry soil. So, we are getting 25%, and also volumetric moisture content. For calculating the volumetric moisture content, we have to multiply the gravimetric moisture content with the dry bulk density. So, we already calculated the dry bulk density as 1.62, and we are multiplying it with 0.25, or 25% of gravimetric moisture content. We are getting 0.41 or 41%. So, this is the result. So, the ultimately we calculated both gravimetric as well as volumetric moisture content. So, I hope that you have understood this solution. So, let us move ahead and see what are the other aspects of measurement of soil moisture. Now, as I have already told you that in the indirect methods, this Neutron moisture probe or Neutron scattering is very much important. Now, among the there are some radiation methods. If you go back to our previous slides, you can see that the radiation technique, there are two types of radiation technique we generally use. One is Neutron scattering, another is gamma ray attenuation. So, let us talk about the Neutron probe. We call it Neutron moisture probe also. So, this is the picture of Neutron moisture probe, and basically in the Neutron moisture probe, the probe is basically lowered. So, this is the soil surface, and we generally lower the probe. Now, before lowering the probe, we have to install this access pipe. Now, this access tube is basically made of some metal, and basically this Neutron moisture probe is lowered into a soil via previously installed access tube, and it contains a source of fast neutrons and a detector of slow neutrons. So, this probe contains a source of fast neutron as well as a detector of slow neutron. Now, once we insert this probe into the soil through these accept tubes and generate the neutrons, these neutrons will collide with the hydrogen atom. Now, how these hydrogen atoms generated? These hydrogen atoms are basically coming from the nearby water molecules. So, once these neutrons are neutrons collide with these hydrogen atoms of the water molecules, the neutrons further slow down and scatter, and we call it thermalized neutrons. The slow neutrons are called thermalized neutrons, and the number of slow neutrons or thermalized neutrons counted by a detector, which is also present in this probe, and this basically corresponds to the soil water content, and by this you can calculate the soil moisture or soil water content. So, this is the principle, or this is the working principle of this Neutron moisture probe. So, let us see what are the, this is a very efficient method, but it has got some drawbacks also. So, let us see what are the drawbacks of Neutron moisture probe. First of all, for operating a Neutron moisture probe, you need a radiation permit. Secondly, it is very much expensive instrument, and thirdly, it cannot be used in a high organic matter or high organic matter rich soil. And finally, it requires an access tube. So, obviously, you can see there is a although the probe housing contains all the detector, neutron generators and detectors and all these things. However, you have to pre-install a access tube, and this access tube will be required for measurement of moisture content through this Neutron moisture probe. The another method is called TDR or time domain reflectometer. The time domain reflectometer works on the principle of time domain reflectometry. Now you know that a dielectric material is poor at conducting electrical current. However, it can support an electrostatic field, something like a magnetic field. And instruments, basically the time domain reflectometer, which operates the principle of time domain reflectometry, it can measure the dielectric properties of soil, which can be used to determine the proportion of the soil volume comprised of water, because you know that the dielectric constant, because of the fact that dielectric constant of water, which is basically 18, is far greater than other mineral particles. Or for air, generally in case of mineral particles the dielectric constant varies from 3 to 5, and in case of air the dielectric constant is 1. So you can see the volume, the dielectric constant in case of water is far greater, and therefore the dielectric constant for the whole soil is nearly proportional to the volume of water in the soil in the immediate vicinity, that is 3 to 4 centimeter of the sensor. So using this working principle, this TDR basically works, and it can basically measures the moisture through its dielectric constant. There is a stark difference of dielectric constant between soil moisture and other particles and air. So you can see these are the pictures of time domain reflectometer. Remember that this time domain reflectometer measures both soil moisture content and salinity. So this is very important to remember. And another important instrument for measuring the soil water, or I would say matric potential, rather specifically it is a matric potential. So it is called tensiometer or field tensiometers. Now you can see this is a field tensiometer, and what happens, it is basically a water filled tube. This is a water filled tube, this tube is a water filled tube, and water filled tube closed at the bottom with a porous cup. So this is a porous cup, and at the top is a airtight seal. So there is a airtight seal, you can see, and the tenacity with which the water is attracted to the soil particle is an expression of soil metric potential. You already know that, and remember that this tensiometer measures this attraction or tension. So soil or field tensiometer basically measure the soil water tension, and this tensiometer, what is the working principle of this tensiometer? Well, as you know, it contains this porous curve. So once we insert this tensiometer into the soil, so based on the metric potential of soil particles, or based on the metric potential or attraction of water by soil matrix, obviously the water will go away through this, water will release through this porous curve, and as a result of water movement through this porous curve to the soil, the vacuum, there will be a vacuum created at the top of the tensiometer, and this vacuum or air pressure will, or the tension, in other words, will be measured by a gauge which is fitted at the top of this tensiometer. Vice versa, when there is a water movement, when we are applying the irrigation water, the excess of water will further move towards the porous curve, and it will go inside the tensiometer through this porous curve, and as a result further the vacuum will be adjusted, or and the vacuum will be further measured, or vacuum or gauge tension will be further measured by this gauge. So this is the working principle of this field tensiometer. Remember that the field tensiometer basically works at potential range, a metric potential range between 0 to minus 85 kilopascal. So beyond 85 kilopascal of potential or tension, these field tensiometer do not work properly. So we have finished the field tensiometer. Let us see what else. So there is another important instrument, we call it gypsum block. A gypsum block basically operates we also term this gypsum block as electrical resistant block, because it is made of gypsum. We call it gypsum block also. So these electrical resistant blocks are made up of porous gypsum. You know the formula of gypsum, CaSO4 2H2O, which is embedded with electrode, and when we place this gypsum block into the moist soil, the fine pores in the block absorb the water in proportion to the soil water potential, and the more tightly the water is absorbed by the soil matrix, the less likely that water will be absorbed by these probes. And as a result, or in other words, the more tightly the water is absorbed by the soil matrix, less likely it will be, it will be absorbed by the block. So, as a result, the resistance to electricity flow between the between the embedded electrodes in the block decreases because of the changes in the water absorption. And these changes in water, the electricity flow is basically measured by this electrical resistant block, and this is how it works. So, we have covered this. Another important is thermocouple cyclometer. Now, thermocouple cyclometer, remember that this is a picture of thermocouple cyclometer, and thermocouple cyclometer works. It basically measures both matric and osmotic forces. So, in a thermocouple cyclometer, a voltage generated by the evaporation of a water drop is converted into a readout of soil water potential, which is basically the combination of both matric potential and osmotic potential, and it is most useful in relatively dry soils. Another important apparatus is called pressure membrane apparatus. Now, the pressure membrane apparatus is basically used to measure the water content at metric potential, which is as low as minus 10,000 kilopascal. So, up to this range, tensiometer cannot read. Tensiometer is useful only up to minus 85 kilopascal. However, if you want to measure the soil water content at minus 10,000, as low as a potential as low as minus 10,000 kilopascal, you have to use this pressure membrane apparatus. And this pressure membrane apparatus, it basically after application of specific metric potential to a set of soil samples, their soil water content are determined gravimetrically by this pressure membrane apparatus. And this is a very important laboratory tool, and it makes possible accurate measurement of water content over a wide range of metric potential in a relatively short time. So, this is in a nutshell. You can see the tensiometer, how this porous head is inserted into the soil, and the gauge basically measures the vacuum, and electrical resistance block where the meter is attached to the wires, which measures the electrical flow, resistance to electrical flow based on the amount of moisture which is absorbed. And this is Neutron probe. We have already told that this is an aluminum. You can see this is a aluminum access pipe, and the detector unit is inserted, and the radioactive source is there. And similarly, time domain reflectometer or TDR, you can see there are water sensors, and there is a PVC access tube. So, this is in nutshell gives a basic idea about the different methods of soil water content, and this slide shows different pros and cons of different methods. Obviously, this gravimetric method is a destructive method of measurement of water content, and resistant block or gypsum block can be automated, but not sensitive to optimum plant water contents. So, these are some positive or negative attributes, such as tensiometer. In case of tensiometer, as you can see, it is only accurate from 0.1 to 1 kilopascal. It is a limited range. However, pressure membrane apparatus, it can be used for 50 to minus 10,000 kilopascal, and it is used in conjunction with gravimetric method to construct water characteristic curve. So, these are some characteristics of these different methods of different methods of measurement of water content, and you can see which methods are used in the field and which methods are used in the lab. So, this slide will give you a basic overview of different methods of measurement of soil water content. So, we have finished this lecture of measurement of soil water content. Let us start a tutorial focusing on different mathematical problems and solution for soil bulk density and particle density, soil porosity and soil water content. So, let us start with the bulk density calculation. So, you can see the first question is calculate the bulk density of a 400 cubic centimeter soil sample that weighs 575 grams, which is an oven dry weight. So, we have to calculate the bulk density. Now, one thing I must clear that universally we generally will we denote this bulk density as rho B and particle density as rho D. So, so far we are so far we are terming we are denoting this bulk density and particle density by B D and dB and dP. So, up to this slide we are denoting this bulk density by this dB and particle density by dP, but from now on we will be using rho B and rho D for determining for indicating the bulk density and particle density. Now, you can see the solution says that the bulk density here is basically the ratio between mass of solid and the volume of the mass of the soil and the volume of the soil. So, we already know that oven dry weight is 575 grams and the the volume is already given. So, obviously it is 1.44 gram per cc. The second question is calculate the bulk density of a 400 cubic centimeter soil sample that weighs 600 grams and that is 10% moisture. So, we know that is 600 grams which is already contain 10% moisture. So, to know the oven dry weight we have to divide the 600 grams with 1.1. 1.1 comes with 100 plus that 10%. So, 100% plus 10%. So, basically it is 1.1. So, it is ultimately we get the oven dry weight of 545.5 grams and this bulk density is 545.5. We have already calculated the oven dry weight over this total bulk volume of the soil. So, we are getting 1.36 gram per cc. So, this is how we can calculate the bulk density if the soil weight is given and the moisture content is also given. So, let us see what is the next problem. So, the third problem says calculate the volume of a soil sample that is 12% moisture, weighs 650 gram and has a bulk density of 1.3 gram per cc. So, we know that oven dry weight, we know here the moist weight is given, that is 650 grams and it contains 12% moisture. So, obviously, the oven dry weight will be 650 over 1.12. So, it is 580.4 grams. So, this is the oven dry weight and we know that bulk density equal to mass of oven dry weight over the volume. So, from this we can calculate the volume which is 446.4 cubic centimeter. Excuse me. The fourth question is calculate the bulk density of a rectangular soil sample with dimension of 12 centimeter by 6 centimeter by 4 centimeter, that is 15% moisture content and weighs 320 gram. So, the moist weight is given 320 gram, 15% moisture content is given. So, let us first calculate the volume of a soil. So, it is a rectangular soil sample. So, the volume will be 12 centimeter into 6 centimeter into 4 centimeter. So, it will be 288 cubic centimeter. Oven dry weight we can calculate from dividing the moist weight by the total moisture content. So, it is 1.15. So, we are getting 272 grams and ultimately we are getting the volume of the soil. Now, we are getting the oven dry weight. Obviously, we can calculate now the bulk density which is 0.97 gram per cc. So, I hope that this calculation is now we have understood it And so let us go and see what is the next question. The fifth problem is calculate the oven dry weight of a 350 cubic centimeter soil sample with a bulk density of 1.42 gram per cc. Now, we already know the bulk density is 1.42 gram per cc. We do not know the mass of soil. However, we know the volume of the soil, that is 350 cubic centimeters. So, obviously, from that we can calculate the oven dry weight, which is 497 grams. The number 6 question is calculate the porosity of soil sample that has a bulk density of 1.35 gram per cc and assume the particle density at 2.65 gram per cc. Now, we already know the formula porosity, or porosity is basically is 1 minus BD by PD into 100. So, porosity basically expressed in terms of percentage. So, you can see 1 minus BD by bulk density by particle density multiplied by 100. So, we know that here the bulk density is 1.35, the general the average particle density of mineral soils are 2.65 gram per cc. So, we can calculate the porosity, that is 49%. So, now you know how to calculate the porosity from the bulk density and particle density. There is another question, calculate the porosity of a 250 cubic centimeter clot that contains 140 cubic centimeter water when saturated. Now, we know that porosity basically can be expressed as a combination of volume of air plus volume of water over total volume. Now, here we already know that the total volume is 250 cubic centimeter and the volume of air and volume of water is 140 cubic centimeter, because it is says that when the soil is saturated, that means all the pore space are filled by water, we are getting 140 cubic centimeter. So, by using this formula we can easily calculate, that is 56%. Number 8 problem is calculate the bulk density of a soil sample that has a porosity of 45%. Now, here porosity is given, bulk density we have to calculate, and particle density we have to assume that the particle density is 2.65 gram per cc, and we will do all the calculation for 1 cubic centimeter of soil. Now, 1 cubic centimeter of soil we know that and we are assuming that particle density of 2.65 gram per cc. So, here if we subtract 0. Porosity here 0.45%. So, if we subtract 0.45 centimeter from 1 centimeter, we will get 0.55 into 2.65. So, the bulk density will be here 2.65. So, we know that bulk density can be calculated from particle density multiplied by the volume of particles. Now, here the volume of particles is solid is 0.55 and we know the particle density is 2.65 gram per cc. So, by multiplying it we are getting the bulk density of 1.46 gram per cc. So, you can now now I hope that these are clear to you, and now you can calculate different problems related to porosity and bulk density. The last two questions are here. Calculate the porosity of a 250 gram of samples that contain 65 grams of water when 55% of the pores are filled with water. So, you can see here the oven dry weight is 250 gram minus 65 grams. So, it is 185 grams of soil. Volume of soil solids is 185 gram over 2.65 gram per cc. So, it is 69.8 cubic centimeter. Saturated water content 65 cubic centimeter over 0.55. So, it is 118.2 cubic centimeter of water. Total volume of soil, obviously the volume of water content and volume of soil solids. So, the total is 188 cubic centimeter. So, porosity will be volume of air plus volume of water over volume of total. We know the volume of air plus volume of water is 118.2 cubic centimeter, or that is the saturated water content, over the total volume of soil. So, it is 188 cubic centimeters. So, ultimately we are getting porosity of 63%. Final question, what is the particle density of a soil sample that has a bulk density of 1.55 gram per cc and a porosity of 40%. So, we know that formula porosity is equal to 1 minus PD by BD, 1 minus bulk density over particle density into 100. So, we know the porosity is here 40, and by inputting the bulk density we can calculate the particle density, that is 2.58 gram per cc. So, I tried to give you a basic overview of how to calculate different numerical problems regarding the porosity, particle density and moisture content. So, I hope that you have learned something, and we will try to cover several more numerical problems as the course goes on. And I must acknowledge for this numerical problem, the Department of Land and Water Resources of UCA Davis of USA, and their class notes I have used for this for setting these numerical problems. So, thank you, and let us meet with a new set of lectures for week 4. Thank you.